All right, guys, let's take a look here. This problem's almost a little too much like the one we did in the book. But it's leaving out a huge part that was kind of weird, was the in and the out rate. This only has an out rate. It's water's draining. Sounds more like I want that to happen now. At a rate of 48 pi feet, cubic feet per second. So I'm going to worry about that on part B, really. Part A just wants to know what's the volume in terms of the radius. So that really just tells me which direction to go with my relationship between radius and height. So if I draw this situation, I know that this is 60. The radius, of course, is 20 because the whole thing's 40. So when I'm at a situation where I'm just at some height and some radius, I know what their ratio has to be. Right? So if I kind of set it up a little bit different, I set it up H over R has to be 60 over 20. So H equals 3R. Cool. So now I have height in terms of radius. If I plug that function into the volume function, I'm going to have volume in terms of radius. Right? So of course the volume for a cone. So now if I plug in 3R for H, the 3's are going to cancel. So you get pi R cubed. Stop right there for a second. So that's using something they told me in what they're asking me about. This whole thing is about the changing volume. Okay. So now, this is the key. You want to try to create the function that models what you're working with from whatever information they gave you. And as soon as you create that function, you can attack it and start plugging in rates and whatever else you know. Right? So for part B now, at what rate is the radius of the water in the tank shrinking? So what's the question in symbols? The symbols for the question they're asking me is?
You need dr by dt.
Yeah. So they're asking me dr by dt. And they tell me, of course, earlier they told me this. And what's that in symbols? dv/dt. Cool. So they want me to figure out what that is, and I know what that is. Right? And at a time when the radius is 16 feet. So now what's the derivative of this?
You get dv/dt equals 3 pi.
Yeah, 3
pi r dr.
3 pi r squared. I like it. That's the chain rule piece. That's like the dy dx piece from the implicit differentiation section. I'm hoping you see, I mean, the derivatives involved in this are going to be a lot easier because the functions inherently have to be not as freaky as they were in section 3.5. Now I plug in everything I know. I know this is 48. All my units are the same, thankfully, right? 16 feet.
Professor.
Yes.
Since it's a shrinking rate of radius, it needs to be negative, so make that 48.
Yeah. It technically should be negative, but the question says at what rate is it shrinking? So it's sort of inherent. Okay. But nothing wrong with the negative. There. I like it. So it's negative 48 because it's flowing out. That's cool. Equals 3 pi. I know the R.
48 pi.
Yeah. No, the R, the dr dt is. I don't know, but the R is 16.
No, there's 48.
The dv/dt is
48 pi.
Yeah. This.
No.
48 pi. Thank you. Yeah. I put that there on purpose. So my pi's will cancel out, right? And there's one extra thing I want to do with this problem at the end. So of course the pi's cancel out. Divided by 3 is negative 16. Divided by a couple 16s leaves 1/16 on the bottom, right? So you end up with dr dt equals negative 1/16 feet per second. I'll let you guys. All right, this is divided by 3, divided by a couple 16s. Now the funny thing about, so that's part B. And of course the funny thing about part C is, I've got this. I don't want to go through this whole damn thing again, putting r equals 1/3 h in here, getting a function of h, and then doing all this stuff. I could. But I know how h and r are related. I know dr dt now. So I can figure out what dh dt is by using this relationship. So if I take the derivative of this with respect to time, what do you get?
dh by dt.
Yeah, you get dh dt equals
3.
3 dr.
3 dr dt. So the height is changing 3 times as quickly as the radius. Which kind of makes sense if you think about it. So I get,
Negative 3/16.
where am I at? Oh yeah, so there. dh dt equals 3 times negative 1/16, so negative 3/16 feet per second. So let me go one step further with this. Let me show you something kind of cool. And then I think we'll do the other problem next time. Shoot, I've lost my other pen. Everything's important. Let me go one step further with this. What's the volume when the radius is 16? What is the volume? I mean, I'm talking about the radius is 16 feet, right? So what is the volume at that point? Somebody help me out. What's 16 cubed?
4,096.
Do it again.
4,096.
4,000.
96.
Everybody's talking. 4,096. All right, thank you. Cubic feet. Pi. Thank you. And in fact, let's take that even further. What is it? Multiply by pi for us.
12,867.963.
That's good. All right. So cubic feet, roughly. Cool. That's at 16 feet. We just figured out that if I change the volume, if I change the volume by, if I decrease it by 48, actually I could leave the pi there, couldn't I? Sure. Because it's 48 pi. So if I decrease it by, let me do this. If I decrease that by 48 pi, then the radius should decrease by 1/16 of a foot. All right, so let's see what happens. Now, stay with me. I don't know if you guys are with me. So if I change this, it's not going to be perfect because it's a big change. If I wait 1 second, won't it go down by 48 pi cubic feet per second? That's the whole idea here, right? So if I subtract 48 pi, this will leave me with 4,048 pi. Is that cool?
Yeah.
So 1 second later, I've got that much in there, right? Now work backwards for me. What is the radius now? So volume is pi r cubed. Volume is now 4,048 pi. So the pi's cancel. What's the cube root of that?
Should be 1349.3.
Do it again.
1349 and a third, or point.
0.3. Okay. So the radius was, whoa, what happened?
You point.
Wait, okay, let's see.
You said the cube root of what? 48?
Yeah, what happened there? That's the square root. I don't know what that
That's
is.
not right.
Oh, you did like a 1/3 of it.
Yeah.
Yeah.
Do it again.
15.94.
Yeah.
All right, that's much
That's
better.
huge.
No, this is kind of cool. Now watch. And I should have realized that, but I'm just not feeling really well. How much did the radius change by?
3/6.
0.06.
Oh, yeah.
And 0.06, what's 1 divided by 16? 0.06. Right? That's kind of cool. I mean, that's the side of this that you don't see a lot. And I'd love to do this kind of problem and show you exactly what the hell's going on here. And if I looked at the height, if I looked to see how the height changed, of course, it's going to change by 3/16. Because the height is 3 times the radius. So, of course, it's going to change 3 times as much as the radius did. But it's really cool to see that these rates, if you just use the numbers, do the 16 and do what the volume would be a second later, it's going to come out exactly the way that we predicted it would. It went down by 1/16 of a foot. All right. So that's plenty. So we'll do